previous video, it left out a little bit of math in the derivation of this P equals C times e to the kt, the law of exponential growth from this differential equation. So what I'm going to do with this video here is actually derive that equation, right? I'm going to fill in the blank that was left behind here by this purple arrow. Okay, so for this exponential growth model, we've got the following assumption. So we are assuming that the growth rate, or the rate at which a population grows, is directly proportional to the population. Okay, this is what we discussed in that previous video, and it basically means as your population gets older, it reproduces, and then there's more people, bacteria, bears, bugs, whatever, to actually do the reproducing. So this was first talked about by, I believe his name is Thomas Malthus, in about, I want to say it's 1798. Let's see. I'm going to check that real quick. Bam, there he is. So Thomas Malthus, and it's in this book, An Essay on the Principle of Population. Yeah, 1798. Is that what I said? Oh, I did. I got it right. All right. And so here's the differential equation that we spoke about, which is dp dt, that's the population growth rate, is directly proportional, so some constant proportionality, times our population. It is a differential equation which we want to solve, so we are going to separate our variables. It's going to turn out to be like some cross multiplication kind of thing. So I'm going to get this p over to the left side of the equation, dp over p. And I'll get the dt over to the right-hand side of the equation, so k times dt, and integrate both sides. When I integrate the left-hand side, I get the natural log of the absolute value of p. It's basically a du over u kind of situation, right? And on the right-hand side, k is just some sort of constant. It's like a slope, right? And we're integrating that with respect to t, so this should just be k times t. And whatever you do, do not forget your plus c. All right, so far, and now we want to solve this for p. To solve this for p, we got to get rid of that natural log that's mucking everything up. So to do that, we're going to exponentiate, and we'll use our pro technique here with that e to the c business as well, using a property of exponents to simplify it. So on the left side of the equation, we'll have just the absolute value of our population is equal to e to the kt times e to the c, right? Whenever I multiply with like bases, I'm adding the exponents, which is what was happening right up here. All right, and now just out of a matter of convenience, I'm going to take this e to the c, bring it out to the front, and then think about this for a second. Whenever I am talking about a population, it is a perfectly reasonable thing to say that our population is greater than 0, so we don't need the absolute value symbols. It's already going to be positive. So we got p, get rid of the absolute value, not plus or minus, just the positive part, is equal to sum e to the c times e to the kt. And now we're almost there. Now remember that e to the c as a number, it's a constant, and that constant is always, let's see, I'll change the pick here. This constant is always positive and non-zero. So e to the c is greater than 0. Yeah, there you go. It's just greater than 0. It's just based on the graph for e to the x, right? We see this thing right up here, right there. Can't be 0, and it can't be negative. So what we usually like to do is check to see, is p equal to 0 a solution? A solution? Question mark? Because if it is, then I can take e to the c out of this equation, and I can just replace it with a more common constant like, just a c or something. So to check to see if p equals 0 is a solution, I'm going to plug it back into my differential equation, which is this guy right here. All right, and so we need a derivative, and then we need the p. We'll stick both of those things into our differential equation. So our dp dt in this case will also be 0, right? The derivative of 0 is 0. And now we plug both of these things into our differential equation. dp dt is equal to kt, kp, and then check to make sure that that solution works. So in the place of dp dt, we will put a 0. Yeah, that's good. So 0 is equal to, and now finally in the place of p, we'll put another 0, equals k times 0, which leads to the conclusion that 0 is equal to 0, which most of the time that is true. Most of the time. Which means, all of this to say that p equaling 0, population of 0, fits this differential equation. It's a possible solution, which allows us to write our equation, our final equation, as p is equal to c, some constant of proportionality, e, or not constant proportionality because that's this one here, kt. So we're about to see what that c means within the context of this particular exponential growth situation. So speaking of that, in example 1, for p is equal to c times e to the kt, find p of 0. That means the initial population. We're going to plug 0 into this equation and explain what this means in the context of the population growth scenario. Let's check this out. So in this equation, we're going to plug 0 in for RT and see what happens. So I'll have p is equal to c e to the, it'll be k times 0. K times 0 is just 0. E to the 0 is 1, which leads to the conclusion that p is equal to c. What does that mean? That means that this c value that we just found is in fact the initial population, because it was the population that happened at time 0. So this is the initial population. An important conclusion, but it's one that maybe you anticipated, because let's say when we talk about finance, so in finance you've got this model for continuously compounded interest, which is the amount in your account is equal to your principal times e to the r times t, and the p that is in this equation is the same thing as the c that's in ours, which is an initial amount. The principal is the amount of money that you start this whole situation with. Okay, so going back to the slideshow, let's make some good notes here. If y is a differentiable function of t such that y is greater than 0 and y prime is equal to ky, so that means that the derivative of y is directly proportional to y for some constant k, then instead of having to solve that differential equation every single time, we're just going to know that y is equal to c times e to the kt. And some properties of that, we're going to say that the c value that's in there is our initial value of y. If it's in terms of a population, of course, it's the initial population. If it's in terms of finance, it's the initial amount of your investment. K is our constant of proportionality. Now think about this for just a second. What has to be true about that value of K if this is exponential decay? Like if something's getting smaller and smaller and smaller, then the exponent on E has to be negative. And if k is a negative number, then we have exponential decay. And so our population is getting smaller and smaller and smaller. On the other side of that, if your exponent, so in this case your k, is positive, then we have ourselves exponential growth, and our population's getting bigger and bigger and bigger. All right, so notice that I left off a number. We've got less than 0, we've got greater than 0. Well, what about if your k value is 0? Then that means that we have e to the 0, which is just 1, and your population stays at c, which I think means unless your population is able to live forever, I think that means that you have an eventual extinction event. Okay, let's look at the next example. The rate of change of y is proportional to y. When t is equal to 0, y is equal to 2. When t is equal to 2, y is equal to 4. The question's asking, what is y when t is equal to 3? So this is kind of a typical kind of question that I want to understand that y, the rate of change of y is directly proportional to y, what that differential equation is going to be, how it's supposed to solve, and then really that's it for the calculus. The rest of the problem turns into algebra. So let's take a look at this one, and for some reason I've already highlighted stuff on this. Okay, so in this next example, which I'm going to call example 2, it says that the rate of change of y, so y prime, is directly proportional to y. All of that means I want to instinctively just know that that solves as y is equal to c e to the kt, assuming that t is our independent variable, which it is. And now I have some conditions here. I've got an initial condition, I've got another condition, blah, 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 in order for us to be able to solve this problem. So we've got the points 0, 2. Yeah, plug in 0, I get 2. And then I also have another 1, 2, 4. Plug in 2, I get 4. Well, this one is extraordinarily easy to deal with. It's basically our initial amount, and we have already discussed how that initial amount translates to the c value that's right in here. I mean, if you don't remember that, you can just plug in 0 for your t value, a 2 for your y value. You're going to get it anyway. So far, our equation simplifies to y is equal to 2 e to the kt power. And notice that I still have some other constant that I've got to solve for, that constant of proportionality, which is where the second point is going to come in handy. We got 2, 4 that we're going to plug into our equation. I'm going to plug that one in here. This one gets green. Okay, so whenever I plug that one in here, my equation is 4 is equal to 2, that's this 2, not that one, e to the k times 2, or 2 times k. And now we want to solve this equation for k. So to do so, I'll divide by the 2 that's right out in front and get 2 is equal to e to the 2k. Lovely. So you can see how the rest of this is pretty much just algebra. And now we need to get rid of the e so we can get k, and I do that by taking the natural log of both sides. Taking the natural log of the left, oh, I'm on green, yeah. On the left-hand side just stays, it's the natural log of 2 is equal to 2 times k. And then divide the 2 over, or multiply both sides by a half, whatever, that's equal to 1/2 times the natural log of 2. Now I'm just going to do a little bit of simplification. You can leave it like this, it's perfectly acceptable, but as we've seen with some exponent laws, we can take that 1/2, of course, and we can bring it on the inside of this natural log, and that makes that 2 to the 1/2 power, which is the same thing as the square root of 2. So here is our k value. It's the natural log of the square root of 2. So let's put this information together to rewrite our equation, which will look like this. Y is equal to 2 times e to the natural log of the square root of 2 t. There's our equation. Was it asking for that? Probably not, but we needed it in order to answer the question. And the question was, doop, What's y? When t is equal to 3. So we're just going to plug 3 into our equation and see what happens. So y of 3 is equal to 2e to the, boop, natural log of the square root of 2 times 3. And that's pretty much a calculator kind of problem. So let's start a new one here. And I've got e to the natural log of the square root of 2, I think, and then maybe arrow out of that right there, and then times 3. And let's approximate that one, of course. So we get 5.656 or 5.657. 5.657. Da-da-da-da. All right, so the thing about exponential growth goes that it kind of leaves you with the impression that this e number is all over the place, that everything grows by some exponent of e. And the reason why is because that's how we solve like that equation. It's sometimes, though, a matter of convenience. Like, for example, the one that we just solved actually is not an exponential growth involving e. So just to show you that, I'm going to do a little bit of extra algebra here. Y is equal to 2. I'm going to rewrite this like this. I'm going to rewrite it as, in parentheses, e to the natural log of the square root of 2 to the t power, right? Because it's a power to a power is what's happening right here in this equation. And a law exponents, power to a power, you just multiply your exponents together. Okay. And the part that is inside of the parentheses here, those are inverses of each other, which means that they cancel each other out. And what we had was 2 times the square root of 2. E and the natural log will cancel out, leaving me with just the square root. So y is equal to 2 times the square root of 2 to the t, and you can see that what is the base is not really e, it was the square root of 2. It was just in disguise whenever it was written in this form. All right, so that's going to end this video on the derivation of the exponential growth equation with some sort of example. And we're going to pick it up in the next one with some examples involving half-life.